So now let's go through some useful facts about duration. Remember, we know how to calculate it, this weighted average of maturities in a bond, but also it's important to know that the duration of a portfolio is actually the weighted average of the durations of the constituents. Now the reason that this is because, remember, duration is linear. So we can sort of just add all bonds together, add up all their cash flows, add up their present values, I suppose, occurring in each year, and we'll get a formula that looks like the duration formula, but not now for the bond, but for the entire portfolio of bonds. But now let's go through a bit of duration math to real quick answer the rest of these questions. The duration of a zero coupon bond, the duration of a coupon bond, the change in the coupon rate of a bond, the duration with respect to yield to maturity, and maybe interestingly as an aside, the duration of a perpetuity, a bond that actually doesn't come due ever. Alright, so let's model a few useful facts about duration. First of all, what is the duration of a zero coupon bond? So for now, let's set the coupon placeholder to 0. Let's actually say we've got a 3-year bond that gets the coupon in years 1 and 2, and in year 3 gets the coupon plus principal. But if the coupon is 0, this is a zero coupon bond. And let's say the yield to maturity is 6%. Therefore, what is the present value of this bond? Well, let's just add up the present values of these cash flows. We'll take the cash flow in year 1, discount it at 1 plus the yield to the current period. And we're going to do the same thing for year 2 and year 3, except that we need to change the column addresses. So here's the present value of this zero coupon bond, the present value of 1,000, discounted back 3 times at a 6% yield to maturity. Now if we wanted to calculate the duration, we have our maturities of the cash flows right here. What we need to do is we need to assign to them these weights. So remember, the weights are going to be the proportion that each cash flow represents as a portion of the bond's price. So if the year 1 cash flow is 0, what is its present value, first of all? Well, we're going to discount it. Remember, we're going to discount it to the number of periods at which the cash flow occurs. We're going to discount it at the discount rate. Let's actually make this a static reference so that we can drag the whole thing out. This is the present value of the cash flow, and then we need to relate it as a fraction of the overall bond's price. Now it shouldn't surprise us that the weight in year 1 is 0. Oh, we need to make this a static reference as well, don't we? The proportion of the year 2 cash flow is also, of course, 0. And what about the year 3 cash flow? Well, that one is 1. Because in the year 3 cash flow, the future value is 1,000. Its present value is 839.61. And that, of course, represents the entirety of the present value of that bond. So the weight is 1. Now, what is the duration? Remember, it's the sum of the weights times the maturities. So 0 times 1 plus 0 times 2 plus 1 times 3. So the duration of a zero coupon bond is its maturity. Now, what must be true for the duration of a coupon bond? Well, it should be less than that, right? Because remember, it's sort of like the average time to you getting all of your repayment. And if we get some of our repayment up front in years 1 and 2, well, it's going to push the duration down a bit, push us closer to present day. So let's give this bond a coupon of $80 per year. And indeed, now we see that the durations come down. Everything else is the same mathematically, so we won't repeat it simply for the sake of brevity, but you can repeat this process by yourselves. You will see that the duration is indeed now lower. Now, what happens if the coupon rate actually increases? Well, just as a coupon bond has a lower duration than a zero coupon bond, a higher coupon bond should have an even lower duration than a lower coupon bond. So let's increase the coupon from 80 to 100. And let's go back. 2.78. New duration, 2.75. So indeed, you can see that since we're getting effectively more of our repayment earlier, the average maturity of the repayments is now a little bit less. And now let's go back to 80. Let's ask another question. What happens to duration if the yield to maturity increases? Let's take this 6% yield and let's bump it to 10%. Now currently our duration is 2.78. And with a higher yield, it falls to 2.77. Now, what's the intuition behind that? Why would we expect duration to fall? Well, a higher discount rate will affect farther out cash flows more, right? So it'll make them relatively less important and make the upfront cash flows relatively more important, which will again push that average maturity closer to year zero. Now finally, what is the duration of a perpetuity? Now this is more of a math question than an Excel question, but let's think about it here. First of all, what is the price of a perpetuity? Well, we know that, right? So price of a perpetuity is the cash flow over the discount rate. That's the present value of an infinite series formula. We can express that instead as the cash flow times times the yield to the -1, right? That's the same thing as saying cash flow over yield. But the reason that we might want to do this is let's take a derivative of this. So let's actually say dp dy. Well, what's that going to be? The derivative of c times y to the -1, that's going to be -1 times c to the -2. Now, why did we want to do that? Well, this is beginning to look a little bit like the duration formula, right? So what is the duration formula? Let's remind ourselves of that. Duration is equal to dp dy times 1 plus y over p. And remember, that's sort of the elasticity of the price change. I guess this is actually a negative. Thinks this is a formula, but let's not have it do that. So how can we get to this from this? Well, it looks like what we need to do is we need to multiply this -1 times c to the -2 by 1 plus y over p, right? or actually I guess negative 1 plus y over p. So let's do that. If we multiply both sides of this equation by 1 plus y over p, negative, the left-hand side of the equation is going to be duration, right? Just according to the formula. What is the right-hand side going to be? Looks like I forgot the y there. Oh, and since we were actually multiplying by negative 1 plus y over p, I guess this negative 1 will cancel with this negative 1 on the right-hand side. Now, what is our formula for p? Well, we have that just up above in row number 10. Remember, that's c times y to the negative 1. So we've got c times y to the negative 2 times 1 plus y over c times y to the negative 1. In other words, we can actually cancel y to the negative 1 from both sides, getting rid of it here entirely and reducing the exponent, or well, actually I guess adding 1 to the exponent in the numerator. Now we can also cancel the c's from the numerator and the denominator. And then really what we're left with is y to the negative 1 times 1 plus y. And of course we know that y to the negative 1 is really the same thing as 1 over y. So we can say it's just 1 plus y over y. So this is actually a drastic simplification, and in a way a surprising result that the duration of a perpetuity, you know, a bond technically with an infinite maturity, is actually a very simple expression. So then finally, what is the duration of a perpetuity, let's say, that has a yield of 8%? Well, that would be 1.08 over 0.08, or 13.5 years. So, surprisingly, the duration of an infinite maturity obligation is actually quite finite and not even very long, just some 10 years. And of course, the reason is, remember, the longer cash flows occur in the future, the more heavily they are discounted. So some of the cash flows that occur way far out into the future effectively don't really matter very much. Okay. So now let's talk about this issue of convexity. We saw that the linear approximation of price sensitivity with duration is reasonable, but, well, we did see that there were errors because actually the relation is not linear because it's convex. And the convexity of a bond essentially just represents this idea of the curvature of the price-yield relationship, and the relative price response can then better be approximated if we also add this idea of convexity. So what is the formula for convexity? Well, if the duration was the first derivative of price change with respect to yield, it should sort of make sense that the next step to improve our approximation, if you think about sort of like a Taylor approximation from calculus, if we want to capture nonlinearity, we should probably then think about, as a next step, a second derivative. So let's do just that. And in fact, what we see is that the convexity of a bond is the second derivative of price with respect to yield times 1 over price. And that's going to be calculated as, again, the same cash flow present value relative to total value of the bond weights, except that now what we're going to be weighting is a nonlinear transformation of the cash flow's maturity instead of just t as for duration, we're going to weight t squared plus t over 1 plus yield squared. And that gives us a better approximation of the price change of a bond. Now we're still going to keep our linear approximation from duration, and now we're going to add 1/2 times the convexity of the change in times the change in yield squared. So now this is going to let us capture not only the linear, but some of a nonlinear response of the bond's price change to changes in yield. So now let's go back to that same bond that we were looking at price changes for before, a 30-year bond. We start with a yield of 5%. We know that our linear approximation from duration is only so-so. But now if we approximate price changes including the convexity term, we actually see that we do better over a larger region. We still get some deviation of the true price of the bond in blue relative to the forecasted price of the bond, or I should say the change in green, but over a longer range of interest rate changes, we actually make a better forecast than we did just using the linear one. So I would say maybe from about 7.5, so in other words, up 2.5% to down maybe about 2.5%. Now we actually match the bond's prices much more closely. So this is the power of convexity, and this is why it's actually very useful to keep convexity in mind as well as duration. So let's go through a convexity calculation. Let's take that same 4-year coupon bond. Let's say that it has a yield to maturity of 10%. We already worked out what its duration is. Now let's calculate the convexity. Now remember, this is going to be those same weights that we used to calculate duration, so we don't need to recalculate those. The maturity term is now going to be maturity squared plus maturity over 1 plus the yield squared in all cases. Maturities for years 1 through 4. And so now let's actually ask ourselves, what is going to happen to this bond price if the yield to maturity increases to 11%? Let's create a forecast of it using just duration as well as duration and convexity. So let's run through an application of convexity. Let's say we've got our same 4-year bond. It pays a coupon of 80. It's got a duration of 3.56. Let's calculate its convexity using these same weights. Remember, the weights are effectively the proportion that the present value of each of the bond's cash flows is relative to the present value of the bond that we compute by discounting it at the yield to maturity. So the convexity is going to be the first weight times the convexity expression that depends on maturity. So it's going to be 1 plus 1 squared divided by 1 plus the yield, or 1.1, to the second. And now we're going to repeat this for all of the other terms of the bond for all the other cash flows at maturities 2 through 4. So we're really just going to need to change some rows. We're going to need to change the maturities as they go. The yield to the second power doesn't need to be changed. So here is our maturity for the year 3 cash flow, and here is our maturity for the year 4 cash flow. And if we do that, we indeed get our answer that we were expecting, a convexity of 14.13. But what does that actually mean? Well, let's see how we can actually approximate the changes in this bond's price using, well, first of all, the actual truth by calculating the new present value of the bond and comparing the change in present values. But as well, let's actually calculate the approximations using duration and then also duration plus convexity. So first of all, let's note down the original present value. So we're going to take this and we're going to copy it as a number so that this doesn't change. And now let's contemplate a change in the yield to 11%. Oh, but actually before we go messing with that, let's actually save our duration and convexity as well, because remember those are going to change if the yield changes. Let's preserve those. Now let's change the yield. Okay, so these change, but we don't need to worry about them. What we do need to think of is, here's the new present value of the bond. The yield's gone up. Of course, the present value's gone down. Let's actually look at the change in the bond's price relative to the price. So that's going to be new price minus old price over price. This bond dropped by about 3.1% if we actually estimate its value by discounting all the cash flows all over again. Now, what would we approximate that with if we tried to approximate it with duration? Well, remember, this is going to be -1 times the duration divided by 1 plus the original yield, so 1.1, times the change in yield. The yield went from 10% to 11%, so it changed by 1%. Okay, so we see we're reasonably close. In truth, the bond dropped by about 3.1%. With the duration linear forecast, we expected the price change would be would drop by about 3.2%, so we're about maybe less than 10 basis points off. Not too bad. Let's see how much better we do with the convexity term in there as well. So if we use both duration and convexity, we'll actually first take our duration term, because that's going to be unchanged. But in addition to that, we're going to add the convexity adjustment, which is 0.5 times the old convexity times the change in yield squared. And now you see that actually we approximated the true change in prices almost to 5 decimal places of precision. In other words, our error is actually less than 1 basis point, which illustrates just how much better the convexity adjustment actually is in terms of predicting price changes in bonds due to changes in yields. And of course, by doing it this way, this saves us the trouble of discounting cash flows in a whole mess of scenarios, because we can literally just map changes in yields to changes in prices. Good. So remember, since the changes in bonds price with respect to changes in yield are nonlinear, the point of convexity is that we can actually better correct the price change of the bond. In fact, the greater the convexity of the bond, the greater the expected price increase for a decrease in yield, and the smaller the price decrease with respect to an increase in yield, which makes convexity sort of an attractive asymmetry, right? If interest rates or yields oscillate, a really convex bond is going to gain more when yields fall, then it will lose when yields drop. So we may actually expect to see more convex bonds, bonds with a higher convexity, actually being worth more in the market than bonds with a lower convexity.